Tonight, we begin with an image so familiar that most people never think to question it. The solar system, drawn like a neat diagram on a classroom wall. The sun in the middle. The planets arranged outward in a tidy row. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Sometimes Pluto, if the poster is old enough. Everything placed on what looks like one flat surface, as if the planets were marbles resting on a tabletop. And because you've seen that image so many times, your brain quietly absorbed a powerful illusion. You were taught, without anyone saying it directly, that the solar system is basically flat, that the real action happens in one thin disk, that if you flew straight upward, away from the planetary plane, you would almost immediately leave the solar system behind and enter empty space. But that is not what reality looks like. The solar system is not a sheet. It is not a dinner plate floating in darkness. And once you begin asking what lies above it or below it, the comforting image starts to collapse. Because in space, there is no universal up, no cosmic down. Those directions only exist if you choose a reference plane. And even then, what appears empty from one perspective may be full of objects, structures, and motion from another. So tonight, we are going to slowly replace the old picture with a better one, a deeper one, a stranger one. We'll begin with the reason the planets do appear roughly flat. Then we'll move outward into the regions where the neat diagram breaks down, past the asteroids, past Pluto, past the icy outer frontier, all the way to the vast spherical cloud that surrounds the sun for more than a light year in every direction. By the time we are done, the solar system will no longer feel like a flat poster. It will feel like what it truly is, a layered, three-dimensional structure embedded inside a galaxy that has its own plane, its own motion, and its own version of above and below. And perhaps most unsettling of all, we'll discover that the universe itself has no preferred direction at all. So let your thoughts loosen. Let the old picture fade. And let's begin where all of this really began. Not with planets, but with a cloud. Long before there was an Earth, long before there were oceans, continents, or even a sun, there was only a vast drifting cloud in interstellar space. A cold molecular cloud made mostly of hydrogen and helium, with traces of heavier elements mixed through it like invisible dust. Carbon, oxygen, silicon, iron, the raw material of future worlds. Those heavier elements had not existed at the birth of the universe. They were forged inside older stars, then flung back into space when those stars died. In that sense, the solar system began as recycled stardust, the remains of stars that lived and died long before our sun was born. For ages, this cloud may have drifted in a kind of balance, gravity pulling inward, gas pressure pushing outward. But eventually, something disturbed it. Perhaps a nearby supernova sent a shock wave through the cloud. Perhaps a passing star gave it just enough of a gravitational nudge. Whatever the trigger, one region of the cloud began to collapse under its own gravity. And as it collapsed, something crucial happened. It spun. Not dramatically at first, almost imperceptibly. But in the universe, even a tiny rotation matters. As the cloud shrank, its spin increased. This is the conservation of angular momentum, the same principle that makes a spinning skater rotate faster when pulling their arms inward. The smaller the cloud became, the faster it turned. And once that happened, flattening became inevitable. Gravity pulled matter inward toward the center, but rotation resisted collapse in every direction. Material could still fall inward, but it increasingly did so in a preferred plane. Over time, the once puffy cloud became a spinning disk, dense in the center, broad and thin around the edges. At the center, pressure and temperature rose until nuclear fusion ignited. A star was born, our sun. Around it remained the flattened disk of gas and dust called the protoplanetary disk. This was the nursery of the planets. Inside it, tiny grains collided and stuck together. Dust became pebbles. Pebbles became boulders. Boulders became planetesimals. And over millions of years, those planetesimals merged into protoplanets and eventually into the planets we know now. So the reason the solar system looks flat is not because the diagrams are arbitrary. It really did form from a flattened, rotating disk. That part is true, but that truth is only the beginning, because the same process that made the system flat also left behind imperfections, instabilities, and distant remnants. And those are the clues that will lead us beyond the simple picture. When astronomers talk about the main plane of the solar system, they often use a term called the ecliptic plane. This is the reference plane defined by Earth's orbit around the Sun. If you could trace Earth's path through space over the course of a year, then imagine that path expanded into an infinite flat surface. That surface would be the ecliptic plane. It is not a physical object. There is no glowing sheet suspended in space, no invisible wall dividing above from below. It is simply a mathematical reference, a convenient baseline, a way of saying, let's measure everything relative to this. And because the planets formed from the same flattened protoplanetary disk, their orbits ended up roughly aligned with that plane. Not perfectly, but closely enough that the standard diagram looks convincing. The inner solar system especially is remarkably thin compared with its width. Mercury's orbit is tilted by about 7 degrees relative to the ecliptic, Venus by about 3.4 degrees, Mars by roughly 1.85, Jupiter by about 1.3, Saturn by 2.5, Uranus by less than a degree, Neptune by about 1.8. These are all small tilts, which is why, from far away, the major planets seem to lie in one shared disk. But small does not mean zero. Even Mercury, with its modest 7-degree inclination, moves millions of kilometers above and below the ecliptic over the course of its orbit. On a human scale, that sounds flat. On an astronomical scale, it means even the flat part of the solar system has depth. The reason these tilts exist is simple. The young solar system was not calm. It was crowded, hot, violent, and full of collisions. Growing planets tugged on each other. Massive bodies migrated. Jupiter, in particular, with its enormous gravity, likely influenced the architecture of everything around it. Small irregularities became permanent features of the system. So the solar system did not settle into a perfect disk. It settled into an almost disk, a thin one, a structured one, but not a flawless one. And that distinction matters, because once you stop imagining the solar system as perfectly flat, your mind becomes ready for the next step. The realization that the major planets are only the most orderly part of a much larger, much stranger structure. A structure in which inclinations increase, orbits become eccentric, and the flat picture begins to unravel. The planets are the calm center of the story. The deeper mystery lies farther out. On Earth, up and down feel obvious. Down is toward the ground, up is toward the sky. Gravity gives those directions such consistency that they seem universal. But they are not universal. They are local. If you are standing in Amsterdam, your down points toward Earth's center. If someone stands in New Zealand, their down also points toward Earth's center. But those directions are not parallel. They point in almost opposite directions through space. Two people on opposite sides of Earth each feel upright, even though their ideas of up and down are reversed relative to one another. That alone should tell you something profound. Up and down are not built into the universe. They emerge from local gravitational conditions. And in space, far from a planet's surface, those conditions change. Drift far enough from Earth, and there is no natural floor beneath you, no ceiling above you. You can rotate however you like, and every orientation is equally valid. So when we ask what lies above or below the solar system, we are already making a choice. Above, relative to what? Earth's orbit? Jupiter's orbit? The total angular momentum of the solar system? The plane of the galaxy? Most of the time, the answer is the ecliptic plane. Above means north of that invisible surface. Below means south of it. This is useful, but we should never mistake usefulness for absolute truth. The ecliptic is a reference, not a law of nature. Astronomers also use another plane called the invariable plane. This is defined not by Earth's orbit, but by the total angular momentum of the solar system as a whole. Because Jupiter dominates so much of the solar system's orbital momentum, the invariable plane lies close to Jupiter's orbital plane and is tilted slightly relative to the ecliptic. That means even within our own solar system, there is more than one legitimate flat baseline. So the question of what lies above or below the solar system is already more slippery than it first appears. We are not asking about a cosmic floor and ceiling. We are asking what exists on one side or the other of a chosen plane, a plane that is mathematically convenient but not physically sacred. This matters because once you accept that above and below are relative, the old picture loses its authority. There is no privileged viewing angle, no single correct poster, only perspectives. And from some perspectives, the solar system looks quite flat. From others, it looks like a layered cloud. And from far enough away, it stops looking flat at all. If you zoom out and look only at the 8 major planets, the solar system really is astonishingly thin. From Mercury's average orbit at around 58 million kilometers from the Sun to Neptune's at roughly 4.5 billion kilometers, the main planetary system spans a tremendous width. Yet its vertical thickness, measured by how far the planets rise above or dip below the ecliptic, is tiny by comparison. Even Mercury, the most inclined major planet, only reaches a few million kilometers above or below the shared plane. That sounds enormous, and it is, but relative to the full width of the planetary system, it is remarkably small. The planetary region is hundreds of times wider than it is thick. If you scaled it down, it would resemble something closer to a sheet than a sphere. This is why textbooks get away with the flat drawing. For the major planets alone, the simplification is not outrageous. It captures the broad geometry of their motion. It tells a mostly true story, as long as you don't mistake it for the whole truth. But simplified images are powerful. They don't just leave things out. They train the imagination. And when you spend years seeing only the thin planetary disk, you begin to assume the rest of the solar system must be similarly arranged. You begin to think the disk is the system. It isn't. The disk of planets is more like the inner floor of a giant structure, the most orderly layer, the part closest to the original protoplanetary disk, the part still dominated by the same flattened geometry from which it formed. Yet even here, there is motion and subtle complexity. Orbital planes slowly precess over time, wobbling under the gravitational pull of other planets. The ecliptic itself shifts over long time scales. The Sun is not fixed either. It moves around the center of the Milky Way and carries the planets with it. The whole disk is dynamic, not static. So even the thinnest, calmest part of the solar system, is more alive than the poster suggests. Still, compared with what comes next, the planetary disk is almost serene, a kind of geometric memory of the solar system's birth. Because once we move beyond the planets, especially beyond Mars and Jupiter, we begin to meet objects that do not stay politely near the plane. Their paths arc upward, downward, sideways. Some tilt steeply, some loop wildly, some move in reverse. And those objects reveal that the flat disk is not the solar system itself. It is just the center line. Between Mars and Jupiter lies the asteroid belt, and at first glance, it seems like it should fit neatly into the same flat story. A broad ring of rocky leftovers orbiting the Sun in roughly the same region. And in a general sense, that is true. Most asteroids do orbit near the ecliptic. They still carry the memory of the ancient disk from which they formed. But this is where the simple picture begins to crack. Unlike the major planets, many asteroids have much larger orbital inclinations. Instead of staying tucked neatly near the central plane, some travel noticeably above and below it. Their orbits reveal that the solar system's vertical structure becomes more obvious even within regions we often imagine as flat. One of the most dramatic examples is Pallas, one of the largest asteroids in the main belt. Its orbital inclination is about 35 degrees. That is enormous compared with the planets. If the major planets are moving around the Sun on paths close to a tabletop, Pallas is circling on a tilted ring that leans steeply upward and downward through space. Ceres, the largest object in the asteroid belt, and classified as a dwarf planet, also does not lie perfectly in the shared plane. Its inclination is over 10 degrees. Vesta, another major asteroid, is tilted by about 7 degrees, close to Mercury's value. These are not tiny deviations hidden by scale. They are genuine departures from the flat image. And the reason they matter is not just geometric. They reveal history. The asteroid belt is not a quiet museum of untouched relics. It is a region shaped by gravitational disturbances, especially from Jupiter. Resonances with Jupiter's orbit can destabilize asteroid paths, pump up their eccentricities, and alter their inclinations over long periods. The belt is a place where order and chaos mix, a place where some bodies remain fairly close to the old disk, while others are scattered into more extreme trajectories. If you drew the asteroid belt honestly in 3 dimensions, it would not look like a perfectly smooth ring. It would look like a thickened zone, a population with depth. Some bodies near the midplane, some arching high above, some diving far below. So here, long before we reach Pluto or the outer frontier, the illusion of flatness is already failing. The textbook diagram works only by filtering. It highlights what stays near the plane and ignores what doesn't. It teaches neatness by omission. And once you see that, you begin to notice a pattern. The farther outward you go, the wider the range of orbital tilts becomes. The solar system is starting to puff upward. For decades, Pluto sat at the edge of the solar system, like a quiet afterthought, a small frozen world placed neatly at the end of the planetary lineup. It looked like it belonged there, like the final dot on a straight line. But Pluto was never actually part of that line. Its orbit tells a completely different story. Unlike the 8 major planets, Pluto doesn't stay close to the ecliptic plane. Its orbital inclination is about 17 degrees. That's more than double Mercury's tilt, which is already the highest among the main planets. And while 17 degrees might not sound dramatic at first, in the scale of the solar system, it is enormous. At its highest point, Pluto rises more than 1 billion kilometers above the planetary plane. Then, over the course of its long orbit, it dives just as far below it. It spends half its time above the ecliptic and half below, not gently wobbling like the planets, but sweeping through space at a steep angle. If you could view the solar system from the side, the planets would appear as a thin glowing band, a narrow line of motion centered around the sun. And then Pluto would cut through that band like a tilted ring, crossing it, leaving it, returning again. It doesn't follow the flat structure, it pierces it. And there's something else. Pluto's orbit is not just tilted, it's stretched, highly elliptical. At times, it comes closer to the sun than Neptune. At other times, it drifts far beyond it. Its path doesn't resemble the near circular stability of the planets. It feels more like a wandering loop, drifting through regions the planets never enter. This is why Pluto always felt slightly out of place, even before it was reclassified. It wasn't just smaller, it belonged to a different population entirely. Pluto is not the edge of the planetary system. It is the beginning of something else, a transition point. The first clear signal that beyond the neat disk of planets lies a region where the rules change, where orbits tilt more dramatically, stretch more wildly, where the idea of a flat solar system begins to collapse. And once you notice Pluto's path, really notice it, you can't unsee it, because it raises a question that leads us deeper into the unknown. If Pluto moves like this, what else is out there moving in ways we've never been shown? Once Pluto lost its status as the 9th planet, something important became clear. It wasn't alone. Beyond Neptune, stretching from roughly 30 to 50 astronomical units from the Sun, lies a vast region known as the Kuiper Belt. And Pluto is just one member of this enormous population of icy bodies. At first, you might imagine the Kuiper Belt as simply a wider extension of the planetary disk, a bigger, colder ring of objects orbiting neatly along the same flat plane. But that's not what it is. The Kuiper Belt has thickness, real, measurable, undeniable thickness. Some objects in this region do stay close to the ecliptic. These are known as the cold population, and their orbits remain relatively calm and flat, almost like a distant echo of the original protoplanetary disk. But there is another population, a hot population, and despite the name, it has nothing to do with temperature. It refers to motion, to energy, to chaos. These objects have orbital inclinations that can reach 20, 30 degrees or more. They don't sit quietly in a thin ring. They move above it, below it, through it. Their paths form a thick, extended structure, more like a swollen band or a donut than a flat disk. If you could see the Kuiper Belt from the side, it would not look like a clean line. It would look like a clouded layer, a region where order is fading. And the reason for this is written in the solar system's past. When the giant planets, especially Neptune, were still migrating to their current positions, their gravity disturbed this region. Objects were pulled, scattered, nudged into new paths. Some were pushed outward. Some were trapped in orbital resonances. Some had their inclinations increased, lifting them far above and below the original plane. This is why Pluto itself is locked in a stable orbital resonance with Neptune. It's not random. It's the result of a long gravitational history that shaped the entire outer system. And Pluto is not the only one. Other large Kuiper Belt objects, like Haumea and Makemake, also follow tilted orbits, some reaching nearly 30 degrees. Each one another reminder that the farther you move from the sun, the less the solar system resembles a flat structure. It begins to expand, to thicken, to lose its alignment. The Kuiper Belt is the first place where the solar system stops pretending to be flat. It's where the disk starts to blur into something deeper. And beyond it, the structure doesn't just thicken, it breaks completely. If the Kuiper Belt is where the flat picture begins to blur, the scattered disk is where it falls apart. This is not a calm region, not a stable ring, not even a thickened version of the same structure. The scattered disk is what remains after chaos. It's a population of objects that were violently thrown outward by the gravity of the giant planets, especially Neptune. These bodies didn't settle into neat, repeating paths. They were scattered, pushed into elongated, tilted, unpredictable orbits that stretch far beyond the orderly regions of the solar system. Some of these objects travel on paths that take them hundreds of astronomical units away from the Sun. Their orbits are not just wide, but stretched. At one moment, they drift through the outer edges of the planetary region. At another, they disappear into deep darkness, far beyond anything shown in textbooks. And their inclinations? They are extreme. 30 degrees, 40 degrees, sometimes more. These are not gentle tilts. These are orbits that cut sharply through the solar system, rising far above the ecliptic, then plunging far below it again. If the planets trace a thin glowing band, scattered disk objects move like wild arcs slicing through that band from every direction. One of the most famous examples is Eris. Eris is slightly more massive than Pluto, and its orbit is tilted by about 44 degrees. That's nearly halfway to being perpendicular to the planetary plane. At its most extreme, Eris travels billions of kilometers above and below the ecliptic. It doesn't just drift outside the flat system, it escapes it. And Eris is not unique. There are many objects in the scattered disk with similar or even more extreme paths. Some are so distant and faint that we've likely only discovered a small fraction of them. Most of this population is still hidden in the dark, far from where we usually look. Because here's the key detail. Most telescopes search near the ecliptic. That's where the planets are. That's where we expect things to be. But the scattered disk doesn't care about our expectations. It exists in 3 dimensions. It fills space above and below the plane we chose as our reference. And because of that, much of it remains unseen. This region reveals something essential. The solar system is not just expanding outward, it is expanding vertically. The farther you go, the less the original disk matters. The weaker the sun's grip feels. The easier it becomes for objects to drift into strange, tilted, elongated paths. The scattered disk is not a ring. It's the beginning of a transition from structure into something far more vast and far less flat. Beyond the scattered disk, the structure of the solar system becomes even stranger. Here, we encounter objects that are no longer strongly controlled by Neptune, objects whose orbits suggest something else shaped them, something more distant, more subtle, or more ancient. These are often called detached objects, and the name says everything. They are detached from the main structure of the solar system. Their orbits do not dip back into the region where Neptune can influence them. Their closest approach to the Sun, their perihelion, remains so far out that the giant planets can no longer easily disturb them. They move on paths that feel isolated, almost independent from the rest of the system. One of the most famous examples is Sedna. Sedna follows an orbit so vast that it takes over 11,000 years to complete a single journey around the Sun. At its closest, it is still far beyond Neptune. At its farthest, it reaches distances approaching 1,000 astronomical units. To put that into perspective, Neptune orbits at about 30 astronomical units. Sedna goes more than 30 times farther. Its path stretches deep into a region where the sun's gravitational influence is still present, but incredibly weak. A region where even small disturbances from passing stars or the slow pull of the galaxy itself can reshape an orbit over time. And while Sedna's inclination is not as extreme as some scattered disk objects, its sheer distance gives it something even more important: isolation. It occupies a volume of space so large that the idea of a flat solar system becomes almost meaningless. The ecliptic plane still exists as a reference, but out here, it has lost its authority. There is no clear disk, no dominant alignment, just vast, sparsely populated space. Other detached objects, like 2012 VP113, show similar behavior: large, distant, and orbiting in regions that feel disconnected from the gravitational architecture closer to the Sun. And these objects raise a question. If Neptune didn't put them there, what did? Some possibilities are subtle. Over billions of years, the combined gravitational effects of many small interactions could slowly reshape orbits. Passing stars in the Sun's distant past may have nudged objects into these extreme paths. Even the gentle pull of the Milky Way itself, the galactic tide, can slowly alter orbits at these distances. But there is another possibility, a hidden one. Some astronomers have proposed the existence of a distant, unseen planet, a massive body far beyond Neptune, quietly shaping the orbits of these detached objects through its gravity. This hypothetical world is often called Planet 9. It has never been directly observed, but the strange clustering of certain distant orbits suggests that something might be out there. Something large, something distant, something orbiting far above and below the familiar plane. Whether Planet 9 exists or not, the detached objects already tell us something profound. By the time you reach this region, the solar system is no longer a disk. It is no longer even a thickened structure. It is becoming something else entirely, something that extends in all directions, and soon that transformation will be complete. Up to this point, there's still a faint memory of flatness. The planets stay close to the ecliptic. The Kuiper Belt thickens it. The scattered disk stretches it. Detached objects begin to ignore it. But comets erase it completely. There are two broad types of comets, and each tells a different part of the story. Short period comets, those that return every few decades or centuries, mostly come from the outer regions we've already explored, the Kuiper Belt and the scattered disk. Their orbits are often somewhat tilted, sometimes even dramatically so, but many still retain a loose connection to the ecliptic plane. They are part of the transition. But long-period comets are something else entirely. These are the comets that appear once, blaze across the inner solar system, and then vanish for thousands, millions, or even tens of millions of years. When astronomers track their paths, something astonishing emerges. They come from everywhere, not just from above the ecliptic, not just from below it, but from every possible direction in space. Some approach from steep angles. Some fall inward from nearly perpendicular paths. Some even orbit in reverse, moving backward relative to the planets. A famous example is Halley's Comet. Its orbit is tilted by more than 160 degrees, meaning it doesn't just deviate from the planetary plane. It flips direction entirely. It moves around the sun opposite to the planets, slicing through the solar system like a visitor from a different geometric reality. And Halley's Comet is not unique. Many long-period comets behave this way. Their inclinations span the full range from 0 degrees to 180 degrees. Their paths are not clustered around a plane. They are scattered across all orientations. And this leads to a simple, unavoidable conclusion. If objects are arriving from all directions, then their source must exist in all directions. A flat disk cannot produce that pattern. A thick ring cannot produce that pattern. Only a sphere can. Comets are not just icy wanderers. They are messengers. They are evidence. Each one that appears in our skies is a clue pointing outward, a sign that far beyond the tilted orbits and stretched paths we've already seen, there exists a structure that surrounds the solar system completely, above, below, and everywhere in between. A structure so vast that it redefines what the solar system actually is. Because once you follow the path of these comets back to where they begin, you arrive at something that no flat diagram could ever show you. A sphere of darkness, a cloud of distant, frozen worlds, waiting in every direction. Follow the comets far enough back, and the flat solar system disappears completely. In its place, something far larger emerges, a structure that does not lie along a plane, a structure that does not favor any direction, a structure that surrounds the sun entirely. This is the Oort Cloud, and it changes everything. Unlike the planetary system, unlike the Kuiper Belt, unlike even the scattered disk, the Oort Cloud is not a disk at all. It is a vast, spherical distribution of icy bodies extending in every direction from the sun. Above the ecliptic, there is Oort Cloud. Below the ecliptic, there is Oort Cloud. To the sides, the same. There is no preferred orientation anymore. The idea of above and below begins to lose its meaning. The Oort Cloud is believed to begin thousands of astronomical units from the sun and extend outward to distances approaching 100,000 astronomical units. That's roughly 1.5 to 2 light years, nearly halfway to the nearest star. To understand the scale, imagine this. If the orbit of Neptune were the size of a coin in your hand, the outer edge of the Oort Cloud would be tens of meters away. You would have to walk across a field just to reach the boundary of your own solar system. Everything you've ever seen in a diagram, the planets, the asteroid belt, the Kuiper Belt, would fit inside a tiny region near your feet. The real solar system is not that small drawing. It is this enormous sphere, a sphere filled with trillions of icy bodies, most of them small, dark, invisible, separated by vast distances, drifting slowly in the sun's distant gravitational reach. And you would not see them. If you were placed inside the Oort Cloud, you would feel alone, completely alone. The nearest object might be millions of kilometers away. The sun itself would appear as just another bright star in the sky, not dominant, not overwhelming, just one point among many. This is why we have never directly seen the Oort Cloud. We know it exists because of the comets, because of the patterns they trace, because of the way they arrive from all directions, carrying the signature of a spherical origin. The Oort Cloud is not something we observe directly. It is something we infer, but the evidence is overwhelming. And once you accept it, the mental image of the solar system changes forever. The flat disk of planets becomes just the innermost layer. The Kuiper Belt becomes a thickened ring around it. The scattered disk becomes a chaotic extension beyond that. And surrounding all of it, a sphere, a vast, silent sphere. This is what truly lies above and below the solar system. Not emptiness, not nothing, but more solar system, stretching outward in every direction until the sun's gravity finally fades and the stars begin. If the Oort cloud defines the true shape of the solar system, then the next question becomes unavoidable. Where does it end? The answer is not as clean as you might expect. There is no wall, no edge, no boundary you can cross and suddenly say, I have left the solar system. Instead, the solar system fades, slowly, gradually, almost imperceptibly. As you move outward through the Oort cloud, the sun's gravitational grip becomes weaker and weaker. Objects are still bound to it, still orbiting it in vast, slow paths, but the pull is fragile. At these distances, even a small disturbance can change everything. A passing star, the combined gravity of the galaxy, even subtle tidal forces stretching across space. All of these can influence objects at the edge of the sun's reach. Eventually, you reach a distance where the sun's gravity is no longer dominant, where other stars begin to compete, where the galaxy itself becomes the stronger influence. This is not a sharp line. It's a transition zone, a region where an object could just as easily drift away from the sun as remain bound to it. Beyond this point, space is no longer ours. It becomes interstellar. But even before you reach that far, there's another boundary, one that is often misunderstood: the heliopause. This is the point where the solar wind, the constant stream of charged particles flowing outward from the sun, is stopped by the interstellar medium. It forms a kind of bubble around the solar system. Spacecraft like Voyager 1 and Voyager 2 have crossed this boundary. They have entered interstellar space in terms of particles and radiation, but they have not left the solar system. Not really. They are still deep inside the Oort cloud's domain, still under the sun's gravitational influence, still tens of thousands of years away from reaching its outer limits. This distinction matters because it reveals just how misleading our intuition can be. We think of the solar system as ending somewhere near the planets, then maybe a little farther out. But in reality, the planets occupy only the innermost fraction of it. The true solar system stretches nearly 2 light years across, a vast sphere embedded in the galaxy. And within that sphere, there are layers: the dense inner region of planets and asteroids, the thickened outer regions of icy bodies, a long, quiet gap, and then the immense, diffuse cloud that surrounds everything. Between these layers, there is emptiness, not absolute nothingness, but something close, a near-perfect vacuum, where distances are so large that even millions of kilometers can separate neighboring objects. If you traveled straight up from Earth, perpendicular to the ecliptic, your journey would take you through all of this. First, the thin planetary disk, then the scattered populations, then the deep silence, then the distant Oort cloud, and only after more than a light year would you begin to truly leave, which leads to a realization that is both simple and unsettling. There is no special direction out, no shortcut upward, no escape downward. Every path outward is long. Every direction leads through the same vast sphere. Above the solar system is not emptiness. Below it is not emptiness. It is the same structure, extending equally in all directions. And beyond it, something even larger awaits. Space continues. So far, we've been asking what lies above and below the solar system, using one reference, the ecliptic plane. But the solar system is not alone. It lives inside something far larger, the Milky Way. And the Milky Way has its own structure, its own flatness, its own version of above and below. The galaxy is shaped like a vast disk, tens of thousands of light years across, filled with stars, gas, and dust. This disk is called the galactic plane. Most of the visible stars in the night sky belong to this structure, forming that faint, glowing band you sometimes see stretching across the darkness. And here's the part most people never consider. The solar system's plane and the galaxy's plane are not aligned. They are tilted by about 60 degrees. That means if you imagine the galaxy as a giant flat surface, the solar system is not lying flat on it. It's angled, like a plate leaning against a wall. So when you say above the solar system, you are pointing in a completely different direction than if you say above the galaxy. Two different ups, two different downs. Both valid, neither absolute. If you travel upward relative to the ecliptic, you are not moving straight out of the galaxy. You are moving diagonally through it, passing through regions filled with stars, gas, and dust. But if you travel upward relative to the galactic plane, you are leaving the dense disk of the Milky Way more directly, moving toward regions where stars become sparse, where space opens up into something quieter and older. This difference matters because it shows just how dependent direction is on perspective. The solar system gives you one orientation, the galaxy gives you another, and both are real. The sun itself sits close to the middle of the galactic disk, not exactly in the center, but not far from it either. It orbits the galaxy at enormous speed, carrying everything with it. The planets, the Kuiper Belt, the Oort Cloud, all of it moves together through space. But the sun doesn't just move in a flat circle. It oscillates. As it travels around the galaxy, it gently bobs up and down through the galactic plane over tens of millions of years, rising above it, falling back through it, then drifting below before being pulled upward again. A slow vertical motion, almost like breathing, and the entire solar system follows. So even if you define above using the galactic plane, that direction is not fixed forever. Over time, the solar system itself moves relative to it. What is above now was not above in the distant past, and will not be above in the far future. Everything is shifting. Everything is in motion. And once you see this, something subtle happens to your understanding. The idea of a stable cosmic orientation begins to dissolve. There is no fixed up, no permanent down, only structures within structures, planes within planes, each one meaningful in its own context, each one temporary on cosmic timescales. And above all of them, if you continue outward, past the Milky Way, past its stars, its gas, its dust, and even its invisible halo, you arrive somewhere even quieter, intergalactic space. This is what lies beyond the galaxy, no matter which direction you choose. Above the galactic plane, below it, or sideways through it. Eventually, every path leads here. And this is where the idea of direction begins to lose meaning entirely. Inside the galaxy, there is structure, a disk, a center, a rotation. You can define above and below relative to that structure. But once you leave it behind, those reference points fade. There is no galactic floor, no galactic ceiling, only distance. The space between galaxies is unimaginably empty. Not perfectly empty, but close. A thin, diffuse gas known as the intergalactic medium stretches across these vast regions, with densities so low that even a single atom per cubic meter is considered typical. To put that into perspective, the best vacuums we create on Earth are still trillions of times denser. Out here, matter is barely present. If you were somehow placed in intergalactic space, far from any galaxy, you would see almost nothing nearby. No stars within reach, no glowing clouds, just darkness. But in the distance, you would see galaxies. Not one, but many. Some faint, some bright, each one a vast island of stars, like the Milky Way scattered across the cosmic ocean. The nearest large neighbor would be the Andromeda Galaxy, a massive spiral drifting toward us across millions of light years. And beyond that, countless others, clusters, filaments, structures on scales so large they stretch across hundreds of millions of light years. This is the true above, when you follow the question far enough. Not just above the solar system, not just above the galaxy, but above everything local. And what you find is not a boundary, it's continuity. Because even here, in the vast emptiness between galaxies, there is no preferred direction. The universe does not have a top or bottom, no edge you can reach by traveling far enough upward. Every direction looks the same on large scales. Every path leads to more structure, more galaxies, more space, and something even deeper. The entire cosmic web, an immense network of galaxy clusters and filaments, extends in all directions, forming a structure so large that individual galaxies become tiny details within it. If you could zoom out far enough, the Milky Way itself would disappear into this web. The solar system would be unthinkably small. Earth would be beyond invisible. And yet, this is still not the end, because even the cosmic web exists within something larger still, the observable universe, a sphere centered on you, not because you are special, but because light has only had a finite time to reach you, a boundary defined not by structure, but by time. And beyond that, we don't know. But what we do know is this: no matter how far you go, no matter which direction you choose, you will never find a ceiling. You will never find a floor. Only more universe. And the deeper you go, the clearer one truth becomes. Above was never a place. It was a perspective. After everything we've explored, the thin planetary disk, the thickened outer regions, the vast Oort Cloud, the tilted position inside the Milky Way, and the emptiness beyond it, one realization quietly settles in. There is no true direction, not in the way you've always felt it. On Earth, direction feels absolute. Down is solid. Up is open. Your body understands it without thinking. Your balance, your senses, even your instincts are built around it. But those directions are not part of the universe. They are part of you. They are created by gravity, defined by your position on a planet, anchored to a surface that gives you a reference point. Remove that surface, and the concept begins to dissolve. In space, far from any dominant gravitational pull, there's no preferred orientation. You can rotate freely, turn upside down, spin slowly, and nothing changes. There is no correction, no natural alignment pulling you back. Every direction becomes equal. And yet, we still talk about above and below, because we need to. We use the ecliptic plane to understand the solar system. We use the galactic plane to understand the Milky Way. We use larger reference frames to understand the motion of galaxies themselves. Each one gives us a way to describe position, a way to map reality. But none of them is fundamentally correct. They are tools, useful, necessary, but not absolute. If you define up as perpendicular to Earth's orbit, you get one answer. If you define it relative to the galaxy, you get another. If you define it relative to the motion of the universe itself, you get something else again. Each perspective is valid. None of them is final. This is one of the quiet truths of physics. The universe does not come with coordinates built in. There is no cosmic grid etched into space. No invisible arrows pointing in the right direction. Direction only exists when you choose a frame of reference. And that choice changes everything. It changes what you call above. It changes what you call below. It even changes how you understand motion itself, because motion is also relative. The Earth spins. It orbits the sun. The sun orbits the galaxy. The galaxy moves through space. At every level, you are in motion, and yet you feel still because your reference frame moves with you. The same is true for direction. You feel upright because your frame defines upright. But the universe doesn't agree or disagree. It simply is. And there is something strangely calming about that. The idea that there is no correct orientation, no fixed perspective, no privileged direction. It means that wherever you are, however you turn, you're not upside down, you're not sideways, you are simply there, floating within a structure that has no top, no bottom, no edge, only depth, only scale, only space extending endlessly in every direction. And in that sense, you are already looking out, no matter which way you face. Now, slowly, bring your attention back from the edges of intergalactic space, back from the vast halo of the Milky Way, back through the immense sphere of the Oort Cloud, back past the distant icy bodies and tilted orbits, back to the thin, quiet disk where the planets move, back to Earth, to where you are right now. If you were to step outside tonight and look up at the sky, everything would feel familiar again. The stars would hang above you. The horizon would sit below. The sense of up and down would return instantly, as if none of this ever changed. And yet, now you know something different. You know that when you look up, you are not looking toward a ceiling. You are looking outward, into one direction among infinitely many. You know that above you is not empty space, but a layered structure, a thin disk of planets, a thickened region of icy bodies, a vast spherical cloud stretching for more than a light year. And beyond that, the galaxy. And beyond that, other galaxies. And beyond that, more space than the mind can comfortably hold. The sky hasn't changed, but your understanding of it has. What once felt like a surface, the dome above your head, is now something deeper. A window, a direction, a pathway into a three-dimensional universe that surrounds you completely. You are not standing beneath it. You are inside it. Every point in the sky is a direction you could travel. Every star is not above you, but away from you. Even the ground beneath your feet is not a boundary. It is simply another direction, blocked by the planet you are standing on. If Earth were transparent, you would see stars beneath you as well. A second sky, just as full, just as vast, stretching downward into the same infinite space. There is no special direction, only your orientation. And this changes something subtle about how you exist in the universe. You are no longer at the bottom looking up. You are at the center of your own perspective, surrounded on all sides by the same cosmos, wrapped inside it, held within it, not beneath the stars, but among them. And as that realization settles in, something else happens. The scale of everything we explored, the distances, the structures, the layers, begins to soften. Not because they become smaller, but because your place within them becomes clearer. You don't need to reach the edge of the solar system to be part of it. You already are. You don't need to leave the galaxy to belong to it. You already do. The same universe that stretches outward for billions of light years is present right here, in the space around you, in the sky above you, in the ground beneath you. It doesn't begin somewhere else. It begins exactly where you are, and continues in every direction. Now the question we started with feels different. What lies above the solar system? At the beginning, it sounded simple, almost like there should be a clear answer. A place, a direction, a destination you could point to and say, There. But after everything we've seen, the answer has changed. Above the solar system is the same thing that lies below it, and beside it, and in every direction you could possibly travel. More universe, more of the same vast structure, unfolding layer by layer. The thin disk of planets, the thickened outer regions, the immense sphere of the Oort Cloud, the tilted position inside the Milky Way, the halo, the void, the distant galaxies, each layer larger than the last, each one dissolving the idea of a boundary. And at the very end of that chain, no edge, no final wall, no place where above suddenly stops. Because above was never a physical location. It was a way of thinking, a habit formed by living on a surface, under gravity, with a sky overhead and ground beneath your feet. A useful illusion, but still an illusion. The universe does not share that perspective. It does not organize itself into up and down. It does not divide itself into top and bottom. It simply exists, three-dimensional, continuous, without preference. And somewhere inside that structure, on a small rocky planet orbiting an ordinary star, a mind emerged that could ask this question, a mind that could imagine above, and then slowly discover that the concept itself doesn't really apply. There is something strangely peaceful about that realization, not disorienting, but freeing, because if there is no true up or down, no correct orientation, no cosmic direction you're supposed to face, then wherever you are, however you are positioned, you are not lost. You are not upside down. You are not misplaced. You are exactly where you can be, surrounded by a universe that extends equally in every direction. And that means something simple but profound. You don't have to look up to see the cosmos. You don't have to search for it in a specific direction. You are already inside it, completely, always. The stars are not above you. They are around you. The galaxy is not somewhere else. It contains you. And the solar system you just traveled beyond is not behind you. It is still here, holding you in its center. As you rest, as you breathe, as you let your thoughts slow down, that vast structure remains, silent, stable, unimaginably large, and yet somehow home. So as the night settles in and the world grows quiet, you don't need to wonder what lies above you anymore, because now you know everything, and nothing different from what lies in every other direction. Just the universe, endlessly surrounding you. Sleep well.